Welcome back, all of you. Since last 2 or 3 classes, you have been trying to understand some of the basic concepts of spin physics. And in the last class, I was telling you about Lormer precision. And in that, I said one of the important concept is the magnetic field will exert a torque inducing motion in the magnetic moment. Torque induced motion will be there in the magnetic moment. This causes spins to precess. I said there are two forces acting on it. One is the applied magnetic field wants the spins to align along its direction, and of course there's a restricted orientation is there. As a consequence, there is a torque which is exerted. The magnetic field will exert a torque inducing motion in the magnetic moment. So millions of such spins will be there, not one or two. They will be rotating. Depending on, because there are spin-off nuclei, two possible orientations like this and like this, which we also understood. We knew the direction of quantization. You could calculate the angle theta in one of the earlier classes. So millions of such nuclear spins will be there, which is in the sample. They all undergo precession simultaneously at the same frequency. So the spins which are oriented in the direction of the field will start rotating like this, and that which orients in the direction opposite to the field, all the spins rotate like this in a cone. They make a cone around the magnetic field. Okay, and of course, this is for the alpha component and this for the beta component. And this precision, I said, is a Larmor precision. It's a Larmor precision. Now the question is, what is its precision frequency? They are rotating, they are precessing. I understand the nuclear magnetic moments are precessing around the magnetic field. But what is this Larmor precision frequency? Of course, it depends on the strength of the magnetic field. Higher the magnetic field, higher the precision frequency. Larmor precision frequency increases linearly with the magnetic field B naught, external magnetic field. And now, as I said, in the current day, we have varieties of spectrometers of various frequencies, up to even 1.2 gigahertz, which is going to come to the market soon, or at least 1 gigahertz and 1 gigahertz I know. So as a consequence, if I say the spectrometer's frequency is 1 gigahertz or 1.2 gigahertz, that is the precision frequency. Imagine the magnetic moments will be precessing at such a high speed. Hertz means cycles per second. In 1 second, it will rotate. In 1 second, it has to rotate 1.2 gigahertz. That is 1.2 10 to the power of 9. Imagine, that is the precision frequency. The spins will be rotating so fast, and it linearly varies with the magnetic field. Of course, again I said, because its precision frequency corresponds to resonating frequency of the spectrometer of the nuclear spins. Earlier I showed you an example where the spectrometer numbers, and the magnet what you see corresponds to resonating frequency of protons, like 300 megahertz, 400 megahertz, 500 megahertz magnets I showed. So if I say I have a spectrometer at 1.2 gigahertz, that means my precision frequency is 1.2 gigahertz. This again tells me NMR is in the radio frequency region of the electromagnetic spectrum. Now, what is the energy involved? Look at this table where varieties of spectroscopic techniques are in the electromagnetic spectrum. Varieties of frequency ranges have been given. And of course, wavelength and frequencies have been classified, which all of you know all these things. And energy is another thing which is important, energy of interaction. If you look carefully, radio frequency comes at the bottom of this table. See, the energy which is highest is cosmic rays, gamma rays. For example, X-ray, energy in kilojoules per mole, if you take it, it is 1.2 into 10 to the power of 4 to 1.2 into 10 to the power of 6. Very large amount of energy. If you come to radio frequency region, energy is very small, of the order of 10 power of minus 3 to 10 power minus 7. Very, very low energy region. NMR spectroscopy falls in the very low energy region. Very, very low energy because, so that means the interaction energy of the nuclear magnetic moments with the external magnetic field is very weak. The weak interaction energy is really the strength of NMR. You understand? The reason is you can monitor even the minute perturbation at the site of the nucleus. As we go ahead, when we discuss more about chemical shapes and couplings, we understand the electronic charge distribution at the site of the nucleus. If there is a minute change because of the substitution, you will see the effect of it. So the weak interaction is really the strength of NMR. We can monitor many interactions at the site of the nucleus. So this is one of the important concepts. Next, I was telling you about gyromagnetic ratio. This gyromagnetic ratio has a sign. Let us say we have a magnetic moment mu and angular momentum p. If both mu and p have same signs, then gamma is positive. If mu and p have opposite signs, then gamma is negative. Okay. So this is a look at this figure. This is a magnetic moment. Okay. Now both spin and this thing both are in the same direction. They are in the opposite direction. This is p and mu. This is when both of them have the same signs. You have gamma greater than 0. In this case, you have gamma less than 0. What is the importance of this gamma? So what? If it is positive or negative, how does it matter for us? It has tremendous implications, especially when you are measuring the couplings. You will know what is the sign of the coupling, which is very important. Or when you are measuring what is called residual dipolar couplings, or if you want to do some detect forbidden transitions involving nuclei with negative magnetic moment like nitrogen 15, the sign of precision is very, very important. Okay, so what happens is the nuclei, there are many examples of the nuclei like nitrogen 15, silicon 29, tin 119. All these nuclei have negative gyromagnetic ratio. The reason you see what is going to happen now is depending upon the sign of gamma, the sense of precision, the normal precision of the spins in the magnetic field is different. Look at this. For gamma greater than 0, the spins are rotating like this. It is shown as clockwise rotation. Whereas for gamma less than 0, you see it is rotating anti-clockwise. So it is rotating in the opposite direction. For example, for nitrogen 15 spins, will always rotate in the opposite direction compared to proton and carbon like that, which have positive gamma. This you have to understand this because this concept will be very useful in designing some, for example, double quantum or triple quantum forbidden transitions which you want to detect multiple quantum transitions involving heteronucleic proton and nitrogen, carbon or nitrogen like that. Then sense of precision will decide the quantum. Okay, that is very important. Next, okay, we have understood something in quantum mechanics, spin physics. Classically, also we got the picture. We know it's a Larmor precision. The Larmor precision increases linearly with the magnetic field. We also understood the sense of precision depending upon the sign of gyromagnetic ratio. It is fine. Now, all these things fine. There is a difference in the energy, everything. But we need to detect the signal. You see, how do you detect the signal? The detection of the signal is nothing but the detection of population difference between two energy levels. Okay. Remember in the earlier class I said there is a possibility of that more spins aligned in the direction parallel to the magnetic field than opposing it. That was the lowest energy option I said. So now we have to find out How many spins are in this direction? How many spins are in this direction? The difference is what you are going to see. You see the problem. You see the problem now. Your NMR signal is nothing but the difference in the spin population between two energy states. Now the question is how these populations are distributed. I know, okay, I will detect the population difference between two energy states. But the next question is how do I know what is the distribution of spin population? I have to understand. That is governed by what is called Boltzmann equation. See, population difference between energy states is governed by Boltzmann equation. Okay. So what is this Boltzmann equation, which defines the population ratio between two energy states? This is simply given by this expression. N alpha by N beta is equal to e to the power of energy difference between beta and alpha states, or Kb into T. K is the Boltzmann constant, T is the temperature. But don't get confused. In some books, it is written as e to the power of minus E beta minus E alpha, depending upon which one is your upper state and which is your lower state. Normally, it is at N of upper state or N of lower state, N beta or N alpha. If I take the ratio in the opposite way, N beta or N alpha, then it is going to be e to the power of minus E beta minus E alpha or K beta, Kb into T, or in other words, in simple form, the ratio of the population is given by e to the power of delta E by Kt, or minus delta E by Kt. In this example, the energy level, the way I have drawn, for me, my lower state is alpha, upper state is beta. So in the conventional way, it will be opposite. So I have written like this. No problem. That is why there is no sign. But doesn't matter. Interpretation is same. The population difference won't change whether you take this way or that way. Okay. How do you calculate depends upon this term. And N alpha and N beta are the population of states alpha and beta. I said delta is the energy. Fine. What is delta E? How do you know delta E? Delta E is nothing but gamma h into B naught over 2 pi. We already found out, what is in the way, while we are trying to get the resonating frequency, we understood what is delta E. Delta E is given by gamma into h over B naught. I mean, it is gamma h cross. H cross is written as h over 2 pi. It's a Planck's constant. All right. So I know delta E. I can calculate delta E because I know gamma, I know H, I know 2 pi, I know B naught. B naught is my magnetic field, which it should be expressed in Tesla. I know what is Kb, Boltzmann constant. It is a Boltzmann constant. This value is also well known. Temperature must be expressed in Kelvin. I know what is T. All the parameters I know. So if only thing is B naught is in my control. The magnetic field strength is in my control. I can vary the magnetic field to any value I want and calculate what is it energy separation, what is delta E, difference in the energy. Okay. Let us try to do that. Now, if if I try to do that and find out the spin populations, it will be like this. There will be more spins in this parallel orientation than anti-parallel orientation. You see that there is small difference I am showing you. This is the delta E difference, and this is plus alpha state. I'm sorry, alpha state plus half, beta state minus half. Okay, are parallel or anti-parallel orientations, and I calculate the delta E. Fine. Now, Boltzmann population tells me there are more spins aligned in the direction of the field than opposing it. That is the definition of Boltzmann. Boltzmann population distribution tells me that. Okay, let us find out. So what are the factors that governs then? If you look at this equation, what are the factors which governs population ratio? One is energy separation, because it is the numerator. Larger the energy separation, this population ratio becomes larger. You understand? When does energy separation becomes larger? It is linearly proportional to magnetic field. So when the magnetic field keeps on increasing, energy separation becomes larger and larger. That's what we saw. Larger the energy separation, then according to this equation, there is a greater the population ratio. The population ratio becomes more and more. That's one point. What is the second possibility? To increase the populations. It is also governed by T, temperature. Temperature is in the denominator. I can vary the T, I can take it to infinity or make it zero. Doesn't matter. I vary the T the way I want. Let us see what happens. If this reduces, this keeps on increasing. So I can control this, I can control this. So both are in my hands. So population difference or population ratio is governed by two important factors. One is the magnetic field, other is the temperature. These two factors govern the population difference. Now, for detecting NMR signal, there must be population difference. If there is no population difference, no NMR, no signal. Okay, you can come across a situation like that. Sometimes it so happens you may come across a situation where there is no population difference at all, but not in the natural situation. You can create artificially a situation by equating spin population of both the states by some way. Experimentally, we can do. I'll tell you how later. That is called a saturation state. You go to a saturation state where there is no population difference at all. That means you will not see signal. So, important factor is you must have greater the population ratio or the population difference between alpha and beta states, larger the NMR signal, the sensitivity is higher. You will detect better signal. So we can play with these two parameters now. Now, how we can play with these parameters, how we can increase the intensity, let us see. Okay. First, let us see what is the real population difference between two energy states if you take the population ratio. Not difference, I'm talking population ratio. Okay. So now, delta E I said gamma into this, I wrote H Planck's constant here, and B naught or 2 pi. Okay, B naught is magnetic field, which I have taken in Tesla, 14 Tesla, and 2 pi. Simply it is a number. Don't have to worry. All the units are properly written here. Okay. Simply plug in these values into the calculator and find out what is delta E. If you find out what is delta E, it turns out to be of this order, 10 to the power of minus 25 joules. That is the energy difference. Okay. Now we know delta E. I know KB. Put it into Boltzmann population ratio equation. N alpha by N beta is equal to e to the power of delta E by KT. Put it there. Now I know KB. I know temperature. If I put this into that equation, the population ratio turns out to be 0.999904. You understand? The population ratio is 0.999904. What does it mean? That means the energy number of populations in both the energy states is more or less same, almost equal. Is it not? It is close to 1. Almost, I would say it's 1. Very small difference in the 6 decimal place. So it's very small value. So the population difference is negligibly small. Okay? We can even work out the number. Okay, at room temperature, let me take the example. 2 million populations I will take. It is much more. You have to go in the Avogadro number very high in this thing. But I will take for understanding purpose. Let us say there are 2 million nuclear spins in a molecule and my magnetic field is 14 Tesla. And my temperature is thermal equilibrium, that means room temperature. You understand? These are the conditions. I know magnetic field, I know temperature, and I Take the example of 2 million populations and I want to calculate the ratio. Okay, I will do that. If I do that, it turns out that population ratio is this much. That's already we worked out. So how many spins are there in the upper energy state? How many are there in the lower energy state? You can find out. If you find out, of course, I made a rough calculation. I didn't go to get the ratio, taking million number and everything. Approximately, I made a calculation and you find out what is the number of spins in the upper energy state, what is the number of spins in the lower energy state, and find out the difference. It approximately matches. I mean, up to third or fourth decimal place, I managed it. And then of course, if I take a big calculator, I can work out. Roughly, mental calculation I did, and this is what the numbers I got. But don't worry, but it won't be very much different. All right. If you want, you can find out. You know, n alpha by n beta is this ratio. If now total number is 1 million, it is simple primary school mathematics. You can work out. Okay. Now, at thermal equilibrium, the spin population of both the energy states are nearly same. That's what it says. And very little difference in populations. What does it mean? In 2 millions, the difference in the population is less than 100, about 95 or 96. That means, imagine if I have to take large number of spins into the taking into account calculate all the spins available in a given sample, find out the population ratio, you hardly detect only few hundreds. The difference is so small, and that is what you have to detect. So that means NMR is highly insensitive technique. The population difference is so small. If you want to detect the NMR signal, it's very difficult for you because it's highly insensitive technique. Then you may ask me a question, what do I do then? How do I use NMR? Don't worry, I'll show you. There are many ways of increasing the sensitivity. Mind you, that small population difference you say is more than sufficient. If we can get that signal, detect that signal, and then do all our experiments, whatever we want, that though the population difference is negligibly small, it is still detectable. Of course, there are ways to increase the sensitivity. We can do that. Number of ways are there to enhance the sensitivity. Okay, I can make the signal intensity more and more by various things. Look at the Boltzmann equation. Now, this is in my hands. This energy separation becomes larger and larger with magnetic field. So, larger the magnetic field, larger the energy separation. So, I will play with the magnetic field now. What happens if I play with the magnetic field? When the field strength increases, delta A increases. But remember, when I have taken this ratio, delta E is larger, the population ratio n alpha by n beta increases. Because this is in the numerator. When population ratio increases, the sensitivity increases. Because we detect the difference in populations. That's all it is. See, simple. What you have to do is keep on increasing the magnetic field maximum possible you can achieve. Then your sensitivity keeps increasing. All right. You may ask me a question. Okay, let us say from 5 Tesla, 2 Tesla, I will take the magnetic field to 20 Tesla. I will increase 10 times the magnetic field. Will it solve a problem of sensitivity forever? That is the next question. How much magnetic field you have to increase? If I increase magnetic field by some number, some ratio, or 2 times, 3 times, or 4 times, how much change will be there in the population difference? You calculate. Same way, in the equation which was given to you, just change the magnetic field and calculate. That I took the example of 2 million populations, 2 million spins. When magnetic field is 0, they are all degenerate states. No population difference at all. It is 0. Now, I'll put this in a small magnetic field, not small, reasonably good, to 2.35 Tesla. It's not a small number. In a magnetic field of 2.35 Tesla, I calculated the population difference. It is only 16. Population ratio is 16, not difference. But I made it as a small number, so I took it as a difference so that when you subtract these two, you will get 16 is the difference. Okay. So population ratio is 16, but I've showing you here as the difference, not the ratio. So please remember this. This is a small number you can work out. I had no time to work out, so I'm giving you this value. Now I increase the magnetic field from 2.35 to 9.4. 4 times I made difference. Population difference become 4 times more. Difference was 16 here, it became 64. Okay, further increase. Another double it. Now from here, from this place to here, now it is 18 times. Okay. Okay. From here to here, I'm sorry, this is 4 times. So here to here, 8 times. So I have increased the magnetic field 8 times. 2.35 Tesla became 18.8 Tesla. But what is the difference of population you are seeing? Only 128. My God, look at the difference you are seeing. From 16 spins difference in 2 million, by increasing the magnetic field 8 times, you made it only 128. What great thing you have achieved. Just from 16 spin population difference, you took it to 128. But you may say it is a small number, but it is significant. As far as the n number detection is concerned, this difference is still significant. Remember, I took only example for this thing, but you have taken the n symbol of molecules and so many nuclear spins will be there. If you calculate, that will be still a small number, but significant enough to see the difference in the sensitivity. Okay, that's one thing. You look at it, what happens? I keep on changing the magnetic field. 7 to 14, the sensitivity goes by 2.3 times by increasing the magnetic field. From 14, I go to 21, so it became 5.2 times. See, remember, let us say if the sensitivity goes by 2 times, your experimental time, the instrument time requirement comes down by a factor of 4. It means, let us say I have a sample. It takes, let us say, 4 hours for me to get a reasonably good signal. If I double the sensitivity, then I require only 1 hour. Imagine the saving of the time. But you have to play with the magnetic field, which is not an easy thing to achieve. Higher the magnetic field, so when you increase the magnetic field, achieving a higher and higher magnetic field is technically highly demanding, not easy. But nevertheless, nowadays the technology is so advanced, we can go to 21, even 24 Tesla magnetic fields are available. The sensitivity can be significantly increased. From here to here, 5 times sensitivity enhancement. 5.2, oh, take 5 times. So your experimental time comes down drastically. Okay. And so this spectrum shows you how the sensitivity goes up by change of magnetic field. See, at 400 megahertz, signal to noise ratio is about 600, but here it is about 1700. Nearly threefold enhancement in the sensitivity just by doubling the magnetic field. See this type of spectrum what you get here, and what is the type of spectrum you got just by doubling the magnetic field. It is a significant achievement. Okay. So now this is as when you play with the magnetic field. What happens with the temperature? Remember, temperature term is in the denominator. Okay, let us play with the temperature. When the temperature is lowered, the power of the exponential increases here, because in this expression I have taken the opposite way. So the power of the exponential increases drastically because this comes down. When it increases drastically means what happens? At low, very, very low temperature, the population ratio will get enhanced. The ratio of these two becomes significantly larger. Understand? So you take this one large number multiplied by this. So in the population of alpha states is significantly large, several orders of magnitude multiplied by population of the beta states. That's what it says. So according to this equation, if I go to very, very low temperature, there is a possibility that I can take, not possibility, there is definitely, I can increase the population in the lower energy state because this number becomes significantly larger and multiply by the spins in the higher energy state. So this will become quite large. Population ratio will definitely increase. So that means the sensitivity will go up. Now you may ask me a question. What happens? I raise the temperature infinitely. Instead of lowering, I keep on increasing the temperature very high. Now put this value. Keep putting higher and higher value for temperature here. And temperature, let us assume it is too large a value, close to infinity. Then, because this is in the bottom denominator, then what will happen? This becomes zero. The exponential power becomes zero. When this indices become zero, then it is e to the power of 0 is 1. What does it mean? N alpha will be equal to N beta. That is, when the temperature keeps on increasing, when it becomes very high temperature, your spin population of both the states are equal. This situation is called saturation. That means there is no population difference at all. All this, both the energy states have equal population if you go to very, very high temperature. That is the situation where no signal will be seen. I hope you're all getting the points now. How to enhance the sensitivity? I've already told you. Play with the magnetic field. We calculate the population ratio. When you double the magnetic field, take it to 4 times. We calculated the number. Though the number appears small, but in the realistic spectrum we saw it is nearly threefold rise in the sensitivity by doubling the magnetic field. At the same time, when the temperature is lower, we know that at you go to very, very low temperature, the population in the lower energy state becomes significantly high. Okay? And as a consequence, the sensitivity also, of course, depends upon gamma, another term. In addition to delta E, and temperature, sensitivity also depends upon gamma. It is given by this equation. Okay. Larger the magnetic field, larger the energy, and higher the sensitivity. Okay. Larger the magnetic field, larger the energy, and higher the sensitivity. Now, what happens with gamma? Higher the gamma, higher the sensitivity. How? I'll tell you now. Okay, so we'll come back and discuss more about sensitivity enhancement or dependence of the sensitivity on gamma. Maybe in the next class we'll discuss. But I hope you're all with me in this class. I think I have not lost any of you. I'm trying to trying my level best to take all of you with me. In this class, I discussed about starting from the Larmor precision frequency. We calculated a lot of things. We found out the sensitivity issue. It depends upon delta E and also T. And we have worked out population ratio using the Boltzmann equation. And we knew how to play with the magnetic field, how to play with the temperature to enhance the sensitivity. Another important factor, the sensitivity also depends upon gamma. What will happen, how it depends upon gamma is one thing which we have to understand. So we'll discuss that in the next class.